this chapter we will be examining analysis techniques in frequency domain. So what we have done up to now, analysis techniques. We examined the parallel elements connection, how does this help to do the analysis, and source transformation, how does this help to do the analysis. And the main analysis techniques, one of them is classical one and the other one is mesh current method and node voltage methods. We have done all that. And the new one is called not general analysis techniques, but the specific analysis techniques. The difference is general analysis techniques do the analysis in order to find all the elements, current and voltages within a circuit. When it is specific analysis techniques, these techniques aim is not to find all the elements, current and voltages. It is just to find one of the elements, current and voltages. One of the element, current and voltage. Why do we need that? So we need to explain this first. In order to say that, before that, why we are calculating all the elements, current and voltages, just a few words just to explain it. Let me explain it. So when you do the calculation of all the elements, current and voltages, then you can compare your results with the limits of the elements. There are some limits about the elements usage interval. Example, some manufacturers produce resistors which run when the power absorbed by this resistor is less than 0.25 watts. That means if the power absorbed by the resistor is more than this, then this resistor is not as explained, described by the definition relation, because it burns. So that means then you've got to calculate all these resistors powers. That means you've got to find all these resistors current and voltage and then make the decision which limits required in order to use that resistor within the circuit. That means when you are buying a resistor, if your calculation result is more than 0.25 watts, you're not going to use the resistor. You're going to buy a resistor of which power limit is let's say 0.5 watts. So according to that limit, so you can change your buying policy, or you can make the decision about which resistor you're going to buy. So that's why we are calculating all the elements, current and voltages. Another subject related to this one is to find out the energy consumed by the circuit. So in order to find that, you've got to find independent sources given to you. Let's say if it is independent voltage source, you've got to find the independent voltage source current in order to calculate the total power consumed by your circuit. So in order to find that current, you've got to find all the other currents. So that means in some cases calculation of all the elements, current and voltages is required. That's why we do that general analysis, and there are the techniques to do that. We explain all that. Now we are coming a new title saying that in some cases, for special purposes, we do not have to calculate all the elements, current and voltages. In which cases? Let's say you are designing a circuit and saying that this circuit works properly. That means does what it is asked for. How you can say that a circuit works properly? So it is one way of saying it is this. A circuit transfers that input signal to an output signal. So if you design circuits, then you're going to apply the input available to you, and then you're going to check the output, whether this circuit transfers the input to the required output. So the only calculation that you've got to do here is to check the output. If the output signal is one of the load, let's say load's current or voltage, so that means you're going to calculate one of the element current and voltage in order to say that circuit works properly or not. So electronic people, they design electronic circuits, so they need such an analysis before doing the total analysis, general analysis that we explained before. Before to do that, we've got to do this business to make the decision whether it is working properly or not. And then we are going to do the full analysis, that means general analysis. So let's go in the subject a bit more detail. What is said here. Analysis by Thevenin-Norton equivalent circuit. In this analysis, only one of the elements current and voltages can be calculated, not all of the elements voltage and current, as done in other techniques that I just explained. Energy storage elements included circuits can be analyzed by this equivalent circuit method in frequency domain, but not in the time domain. If you got L and C type energy stored elements, this type of elements included circuits, you cannot only find out one of the elements current and voltage. That is impossible. But this is now a new advantage of the frequency domain. If we could use this Thevenin equivalent circuit concept in order to calculate one of the elements current and voltages. Another way of saying it, if we are using the state equations, from these equations you cannot find one of the elements current and voltage, because first of all you've got to find out state variables first, and then you're going to find one of the elements current and voltages. But we are saying if you are in frequency domain, so you can directly find out one of the elements current and voltages, like the resistive circuits that we could use this method. We already seen it in the circuit theory course. So that is another advantage of omega domain at the same time. What is equivalent, Thevenin equivalence? So you have seen it already, but what we are introducing in here is LC elements included circuit as well. That means linear circuits, energy storage elements included. So that is a circuit. And assume that there is another part of the circuit. This could be just one element, common circuit, or could be a full circuit. That means has got more than one element. You might call it load as well, load circuit, and the circuit except the load. So what we are saying in Thevenin equivalence case, we are saying this green colored circuit, linear circuit, which has got linear elements in it, the equivalent of it, how many of the elements we have is not important. The equivalent, Thevenin equivalent of it is just two elements connected in serial. One of them is Thevenin voltage, the other one is Thevenin impedance. Since we are in omega domain, I said impedance. In the resistive circuits time domain, it was resistor, Thevenin resistor, so I said impedance here. So when you replace this many elements included circuit with just two elements, this common circuit or this common element or this load, current and this circuit elements current and voltages does not change. Another way of saying it, so assume that you have many elements in here and you have this red common circuit here. When you analyze it, you're going to find out all the elements, current and voltages within that red circuit. What we are saying, if you replace that green one with this Thevenin equivalent circuit, whatever you calculated in this red one will be the same as the calculated in this one. That's why we call those two equivalent. Since it is equivalent, the other elements, current and voltages, are not affected from this interchange. So this is in general what equivalence concept means. When you replace or interchange it with its equivalence, the other elements, current and voltages, does not change. That's why we call it is equivalent. So what is next? How we are going to calculate those two, Thevenin voltage and Thevenin impedance, Thevenin voltage calculation in here, and Thevenin impedance calculation in here, and alternative calculation of Thevenin equivalent, Thevenin impedance is given here. So what we have done in time domain for resistive circuits will be repeated here. Only change here is we are in omega domain. So the method steps does not change for the calculation of VTH, which is Thevenin equivalent voltage, and Thevenin impedance. So let's start from the voltage. What is this Thevenin voltage is? Assume that this AB load is connected to the terminals A and B. If it is open circuit, that means no current passing through the load. Then the current is zero, that means the current of ZTH impedance is zero. How we said so? If you write the Kirchhoff current law equation for the node A, you could see that this current should be equal to this one since they are serial to each other. So this current is zero. If this current is zero, multiplied with the impedance gives you zero voltage. So that means this impedance voltage is zero. If it is zero, then VTH is equal to VAB. So we were looking for a rule how we are going to calculate Thevenin equivalent. So we could see here, you're going to make the terminals, the load open circuit, and find out the voltage or open circuit voltage between the terminals A and B. Since this voltage is zero, it's going to be the same as VTH, so you did the calculation. Whatever we said here will be done in the circuit given to you. This blue area is asked what is the equivalent, Thevenin equivalent circuit of this blue circuit. Then what we are going to do, keep these terminals open circuit and calculate VAB, which is equal to VTH. So this becomes now a problem of a circuit analysis, isn't it? So this circuit is given to us, so that means if I calculate these two elements voltages here, 120 ohm and 10 Vx, the addition of those two voltages gives me VTH. So I'm going to find out this. Okay. Whatever I said here, it is given here. So if you do this calculation, so you're going to end up with that result. That result is going to be a phasor of this voltage. So it's equal to this one if you apply this. So one of way of doing it, so this two is connected in serial, you can do the source transformation, transfer it to independent current source in serial with 12 ohms. 12 ohms becomes in parallel with 60 ohms, so you go back to the source transformation once more. You're going to end up a source in serial with resistor here, so it's going to be just one loop circuit. Do the analysis, you get that result. I can give you a blackboard or whiteboard video for this calculation later on. So what about the second one, Thevenin impedance ZTH calculation. So this is impedance now. How we are going to do it? One way of doing it, we could see it from here. If I make this independent voltage source short circuit, that means the terminals are connected to each other. That means deactivation of the independent source. This voltage is 0. If I apply between the terminals A and B a test independent voltage source, let's say VT, so since this voltage is 0, this ZTH voltage is going to be equal to that VT. If I calculate that IT current, then VT over IT gives me that ZTH. How could I say that? Because consider that when this is short circuit, you apply the VTH here. VTH over ZTH gives you that current, isn't it? So I am saying the opposite. So in here, I short circuited the independent voltage source within the circuit given to us. The circuit given to us is this. So short circuit that, apply at VT here. So we've got this circuit now. So this is a circuit analysis once more. If I am saying calculate that IT, VT over IT gives me that ZTH. So I know what to do. How I am going to get this ZTH, since, okay, when we calculate that IT is going to be something like IT is equal a constant multiplied with VT. Why is that? Because we are saying all the elements, current and voltages depends on independent source, isn't it? So IT is going to be equal something like that. Maybe I can write directly to here. Okay, so I could do that. So it's going to be like that. I am saying. Escape for a while. Oh, okay. Not now. Okay. So what I am saying, IT is going to be equal to a constant coefficient multiplied with VT. Then IT depends on VT. VT over IT gives me ZTH. So this is done. The similar things done in the time domain in the resistive circuit. So easy to do. Alternative to this one, instead of deactivating independent source and applying that VT test independent source here, what we do, we short circuit the terminals A and B. When you short circuit the terminals A and B, that means the voltage is 0, that means you're going to put a wire between these two terminals. Then there's going to be a short circuit current here. If I calculate this short circuit current, VTH over that short circuit current gives me that VTH from here. So whatever I said on the right hand side here, I am going to repeat it on the left hand side circuit. How I am going to do it? Make these terminals short circuit A and B and calculate this short circuit current. So this short circuit current is the summation of this capacitor current plus the current of this resistor. So that means I am going to analyze this circuit and find the ISC. Once I find the ISC, we already calculated VTH here, so this VTH over ISC, VTH over ISC gives you ZTH, so I can calculate that. If you do that calculation, you're going to end up with that this short circuit current phase is going to be this, and the impedance is the ratio of this VTH over ISC, which gives you ZTH, and that value is written here. Finally, what is we mentioned in how we're going to find the Thevenin equivalent circuit. So once you've got the Thevenin equivalent circuit, then you can easily say that what Norton equivalent circuit is, because you can use this source transformation that we already seen that. So this is the load. If you replace this source, which is an independent voltage source in serial with VTH, transferred to independent current source in parallel with ZTH. So this equivalent is called, after the transformation, source transformation, this equivalent circuit is called Norton circuit, Norton equivalent circuit. So this is the Thevenin equivalent circuit, this is Norton equivalent circuit. Conclusion is that whatever load you put here, this load's current and voltage do not change whether you got this Thevenin equivalent circuit or the Norton equivalent circuit. So that is the end of this video then. So close that.